Welcome to another episode of AI 10X brought to you by 10 Leaves.
Always great to be here.
Welcome to you, our listener, and thank you so much for joining us for today's deep dive.
We've got a really exciting one lined up.
We really do. So we're looking at a pretty fascinating excerpt today. It's titled AI 10X: Intelligent Orchestration in Modern Transportation.
Right. And the mission for this deep dive is to explore how artificial intelligence is fundamentally changing mobility.
Exactly. We want to act as your guide today to unpack these core concepts without, overwhelming you with all the technical jargon.
Because if you follow the tech space at all, you already know we're way past the early days of, basic cruise control.
Or lane assist, yeah. We're well beyond that.
Right. Today's source material looks at the broader network effect. We're going to see what happens when the entire mobility grid...
Both the vehicles and the infrastructure.
Exactly, both of them, when they shift away from manual control.
So we're going to look at the actual mechanics of this transition and what it really means for the way you move through the world.
The whole premise of the text is essentially that the way our cities flow is, it's on the verge of a massive structural transformation.
Yeah, and it distills the shift down into two major pillars.
It does. It focuses on the autonomous fleets themselves and then the urban infrastructure they interact with.
So we're moving away from looking at just a single self-driving car in a vacuum.
Totally. It's about a fully integrated systemic overhaul of modern transportation.
Okay, let's unpack this.
Let's do it.
And start with the first major shift highlighted in the material, which is the rise of autonomous fleets.
Right, because it's really easy to get tunnel vision on the vehicle autonomy side.
Just picturing one car driving itself down an empty highway.
Exactly. But the text takes a much wider lens. It highlights three specific systemic benefits that these AI-powered fleets bring to the table.
And those are?
They coordinate routes, they reduce accidents, and they optimize fuel efficiency.
That is a lot of technical weight when you scale those 3 points up to a citywide level.
Scaling it up is exactly the point. Taking the safety aspect first, the text notes that these autonomous fleets reduce accidents.
Right, because right now, under our current paradigm of manual driving, human latency is the biggest issue.
Human latency and error are the primary failure points. It's not just about being distracted by a phone. It's about actual biological limits.
Like reaction times?
Yeah, human reaction times are roughly 3/4 of a second just to perceive a hazard.
Let alone actually move your foot and apply the brakes.
Right. But AI-powered vehicles operate with sensor fusion. They integrate LiDAR, radar, and optical cameras to maintain this continuous 360-degree awareness.
So they don't have blind spots?
No blind spots at all.
Yeah.
And they are processing that environmental data and executing physical commands in milliseconds.
Wow. So just by removing manual control, you systematically eliminate the latency that causes the vast majority of collisions.
Exactly.
And that leads directly into the fuel efficiency metric the source mentions.
Oh, definitely. Because human drivers are incredibly inefficient at managing kinetic energy.
We really are. We over-accelerate, we brake aggressively, we just scrub off speed for no reason.
All the time. So when the text talks about optimizing fuel efficiency, it's referring to the AI's ability to calculate the exact optimal acceleration curve.
To get from point A to point B with absolute minimum energy expenditure.
Like the system calculates the physics of the trip perfectly. But what's fascinating here is the first point the text makes. And I really want to emphasize the word coordinate.
Coordinate.
Yes. The text explicitly says these fleets coordinate routes. This is the crucial leap from just individual autonomy to full network autonomy.
Oh, so.
Well, think about it. If you have 100 self-driving cars on a highway, but they don't communicate with each other...
They're still isolated.
Exactly. You definitely improve safety and individual fuel efficiency, but you still have 100 independent agents making isolated decisions. You haven't actually solved the network problem.
Ah, I see.
But the source text is telling us that these fleets coordinate. They use V2X, which is vehicle-to-everything communication, to work together.
So the AI is looking at the entire fleet.
Yes, and distributing those vehicles across the road network to optimize the entire system's fuel use and safety.
But wait, how does that level of coordination actually differ from the dynamic routing we already have?
What do you mean?
Well, if I open up a navigation app on my phone right now, it looks at traffic data and gives me the fastest route. Isn't that already route coordination?
It's actually the exact opposite.
Really?
Yeah, which is why the text's emphasis on true coordination is so incredibly important. Your smartphone app uses what is essentially selfish routing.
Selfish routing.
Yeah. Say there's a backup on the main highway. The app identifies a faster side street and reroutes you.
Right, which helps me.
But it also reroutes the 200 other drivers behind you to that exact same side street.
Oh,
So the app isn't coordinating the fleet, it's just shifting the bottleneck from one location to another.
completely overwhelming a small street that wasn't designed for that much capacity.
Exactly. True fleet coordination, like the text describes, utilizes swarm logic. The overarching AI distributes the load proactively.
So it splits the traffic up.
Right. It might send 20% of the fleet down one artery, 30% down another, and keep the rest on the highway at a slightly reduced speed.
Just to prevent a secondary jam from forming.
Exactly. It optimizes for the macro flow, not just your individual micro trip.
That distinction makes the scale of this shift much clearer. And I want you, the listener, to really picture this for a second in the context of your daily commute.
It's a very relatable scenario.
Think about the phenomenon of the phantom traffic jam, where you're stuck in stop-and-go traffic for 20 minutes, only to finally get moving again and realize...
There was nothing there.
Right. No accident, no construction, absolutely nothing.
It was just one person tapping their brakes 3 miles ahead.
Exactly. Which caused a chain reaction of human overcorrection that just rippled backward through the traffic flow.
It's infuriating.
Now, contrast that chaotic, localized reaction with a perfectly coordinated, fuel-efficient system.
A completely different world.
A system where the cars are exchanging telemetry data in real time, maintaining mathematically optimal following distances, and absorbing those shock waves before they ever turn into a jam.
And that absorption of traffic shock waves, it exponentially multiplies the fuel efficiency we discussed earlier.
Because they aren't stopping and starting anymore.
Right. When the fleet is communicating and coordinating routes, vehicles don't have to engage in that heavy stop-and-go cycle. They adjust their speeds miles in advance to ensure continuous movement.
Wow.
They can even dynamically platoon,
Grouping tightly together.
grouping tightly together on the highway to reduce aerodynamic drag, which drastically cuts energy consumption. So the coordination of the routes is the mechanism that actually delivers the promised accident reduction and fuel optimization at scale.
We are talking about moving from millions of disconnected data silos, meaning human drivers, to a unified, optimized fleet. But the vehicles themselves are only half of the equation presented in our source.
The other half is just as critical.
Here's where it gets really interesting. Because the text doesn't just stop at the cars. It pivots directly to the city infrastructure.
The AI traffic control systems.
Yes. The text specifically states that AI traffic control adjusts signals dynamically to reduce congestion in real time.
This represents the environment actively adapting to the vehicles, rather than forcing the vehicles to adapt to a rigid, static environment.
And the text specifically contrasts this dynamic system with manual control, right?
It does. If we look at traditional traffic systems today, they operate on incredibly rigid, pre-programmed static timers.
Like a schedule.
Yeah. A civil engineer analyzes historical traffic data, decides an intersection peaks at 5 p.m., and programs a timer to hold a green light for 90 seconds on the main artery.
Regardless of what's actually happening on the ground.
Exactly. It is a completely blind open-loop system. It just executes its programming.
Even those more advanced actuated signals we see today, the ones with the inductive loops buried in the asphalt.
Or the basic cameras on the traffic poles.
Right. Those are still fundamentally reactive. They might trigger a light change if a car pulls up to an empty intersection at 2 in the morning, but they have no predictive capability at all.
None.
They're just reacting to a binary input. Is a car physically sitting on this sensor right now, yes or no?
Exactly. They completely lack spatial awareness and predictive modeling. So when the source text highlights that AI adjusts traffic signals dynamically in real time, it's pointing toward a shift to edge computing at the intersection level.
Meaning the intersection itself is smart.
Very smart. The infrastructure is actively monitoring the flow of vehicles using advanced computer vision and sensor arrays.
It isn't just looking at the stop line.
No, it's tracking volume, speed, and density miles upstream.
Which means it's constantly calculating and recalculating the optimal throughput.
In real time.
So if a major event lets out, like a concert, and there is a sudden, unpredicted surge of traffic heading downtown,
the AI traffic control recognizes that density building immediately.
it doesn't have to wait for a historical schedule to trigger. It just instantly lengthens the green lights on the inbound arteries to flush that traffic through.
It can dynamically alter lane assignments too, or change variable speed limits on the fly to throttle the inbound flow, before it hits the choke point.
It's a fluid breathing system that reacts to reality as it happens.
And the goal of this real-time dynamic adjustment, as the text explicitly states, is to reduce congestion.
Which is huge.
It's a critical point, because congestion is the great multiplier of inefficiency. A manual system reacts to a localized traffic jam by stubbornly continuing its preset light cycle.
Systematically feeding more cars into a gridlocked block.
Right, which just causes the jam to cascade into all the surrounding streets. But a dynamic AI system anticipates the jam.
So it stops it before it starts?
If it sees volume building 3 intersections away, it immediately begins adjusting the downstream signals to create a green corridor, clearing out the congestion before it can even fully form.
That dynamic signaling makes total sense. But it really only hits its true potential when you pair it with the autonomous fleets we were unpacking earlier, doesn't it?
They absolutely rely on each other.
Because you could deploy the smartest, most coordinated swarm of autonomous vehicles in the world. But if they're constantly forced to stop by dumb static infrastructure, you just bottleneck the entire network.
You lose a massive portion of the fuel efficiency and safety gains if the cars have to constantly brake their platoons to accommodate a rigid light cycle.
That synergy is really the core thesis of the source material.
It is. For this modern transportation revolution to actually materialize, the intelligence has to exist in both the vehicle layer and the infrastructure layer.
They have to operate in tandem.
The fleet's route coordination data feeds into the city's traffic control AI, and the city's traffic control AI feeds its signal time predictions back to the fleet.
It's a continuous bi-directional feedback loop.
Exactly.
So what does this all mean? The text explicitly asks about the long-term impact of integrating these two distinct technological pillars.
And it provides a very clear, synthesized answer. The long-term impact is safer roads and more efficient urban mobility.
Safer roads and efficient urban mobility.
If we connect this to the bigger picture, we can see the exact mechanics of how that long-term impact is achieved.
Let's look at safer roads under this integrated model.
We already established that autonomous vehicles drastically reduce accidents by eliminating human error and latency.
Right.
But when you introduce dynamic traffic control, you are engineering the environment to minimize conflict points altogether.
Like the dilemma zone.
Yes. That moment approaching a static yellow light where a driver has to make a split-second calculation to either brake hard or accelerate to clear the intersection.
That causes so many rear-end and T-bone collisions.
A massive amount. But in a fully integrated system, the dynamic AI traffic control communicates its timing intent directly to the approaching autonomous fleet.
Oh, wow.
So the vehicles adjust their approach speeds perfectly. They never even encounter a yellow light. They just seamlessly hit the green window.
The conflict point is entirely designed out of the system.
It doesn't even exist anymore.
And then we have the second half of that long-term impact, which is more efficient urban mobility. The phrasing there is really deliberate.
Very deliberate. It doesn't just say faster commute times.
Right. The concept of mobility implies a holistic view of how an entire urban ecosystem functions.
Exactly. When you mitigate congestion through real-time dynamic signal adjustments, and you optimize fuel and energy consumption through coordinated autonomous routes.
You change the fundamental physics of the city.
You really do.
You, as the listener moving through this environment, you aren't just getting from point A to point B with less friction. The entire economic and physical pulse of the city operates with less waste, less idle time, and less ambient pollution.
That level of efficiency represents a hard break from the past. Just think about the sheer volume of spatial and temporal waste inherent in manual transportation today.
It's staggering. Millions of gallons of fuel burned annually by vehicles just idling at red lights while no cross-traffic is present.
Or the sprawling footprint of vehicles creeping along in stop-and-go traffic, because human drivers just cannot coordinate their acceleration.
Right.
By shifting the heavy lifting of navigation and traffic management to integrated artificial intelligence, the text suggests we're unlocking a level of network efficiency that is mathematically impossible to achieve under manual control.
Because the systems communicate.
They communicate, they anticipate, and they resolve the inefficiencies algorithmically before they ever manifest as physical congestion.
It is an incredibly comprehensive model laid out in just a few key points in our source material. We've explored the network effects of autonomous fleets.
How they use V2X communication to coordinate routes rather than just operating as isolated self-driving cars.
Exactly. We've looked at how they inherently reduce accidents through sensor fusion and optimize fuel efficiency by managing kinetic energy.
We contrasted the rigidity of blind, static traffic timers with the edge computing power of AI traffic control.
Right, the AI that makes dynamic, real-time adjustments to actively reduce congestion.
And we've examined how these two distinct layers merge to deliver a long-term impact of definitively safer roads and highly efficient urban mobility.
The overarching theme tying all of these mechanisms together is the transition away from manual control.
Manual control, by its very nature, is completely disjointed.
It really is. It relies on millions of disconnected human decisions, which makes it inherently inefficient and prone to cascading errors.
What we are moving toward is a fully synchronized ecosystem, which the text perfectly labels intelligent orchestration.
Intelligent orchestration. That is the definitive big takeaway from today's deep dive.
It really is.
Transportation is undergoing a massive structural shift from manual control to intelligent orchestration. It's a phrase that perfectly captures the synergy we've been discussing today.
It elevates the conversation from simple automation.
Which is just a machine doing a human task.
Exactly. Up to orchestration, which
Yeah.
implies multiple complex systems working in perfect concert.
It is the ideal framework for understanding this shift. An orchestra requires both the individual musicians and the conductor.
The autonomous fleets are the musicians. They have to execute their individual parts flawlessly, coordinating their routes and optimizing their movements.
But the AI traffic control is the conductor.
Right. Managing the broader environment, adjusting the tempo of the signals dynamically to ensure the entire system flows without congestion.
Because if you only have smart cars, you just have highly capable musicians playing without a tempo, eventually resulting in a chaotic jam.
And if you only have dynamic signals, the conductor is trying to guide a fragmented manual fleet that simply can't respond with precision.
It's the intelligent orchestration of both layers that creates the seamless urban mobility the text promises.
It fundamentally changes the relationship between the vehicle, the infrastructure, and the passenger.
The friction we currently accept as just a normal part of traveling.
The gridlock, the sudden braking, the idle time.
All of that. Those are all just artifacts of manual control. Intelligent orchestration replaces that friction with invisible algorithmic coordination.
And this raises an important question. A final thought for you to consider as you navigate your own city today.
I'd love to hear it.
We have spent this deep dive analyzing the technological mechanics of how AI is going to perfectly orchestrate our routes and dynamically control our traffic signals to optimize flow.
We understand the digital shift from manual control.
Right. But consider the physical ramifications. If AI is going to perfectly orchestrate our routes and dynamically control our traffic signals, how might this shift from manual control fundamentally change the physical way we design the cities of the future?
That is fascinating.
If we no longer need sprawling multi-lane highways just to act as waiting rooms for congested traffic, what becomes possible in the vast amounts of urban space we suddenly reclaim?
That is a phenomenal question to end on. The shift to intelligent orchestration doesn't just change the way we drive through the city, it will inevitably change the architectural and physical footprint of the city itself. We hope this deep dive has provided you with a much sharper lens through which to view the massive technological transition happening in modern transportation. Thank you for listening to another episode of AI 10X brought to you by 10 Leaves.